In this second lecture, in this set of two, we're going to talk about voltage and capacitance, and we're going to relate these important quantities, and you're familiar with these quantities in a circuit context, but we're going to relate them to the electric field in the field context. You'll see Andre's name on this slide deck. Andre actually prepared this lecture, but I'm giving it. The learning objective from this lecture is that a student, at the very least, should be able to understand the connection between the electric field, which is the fundamental quantity that we care about in electrostatics, and this voltage or potential difference, which is a tool that we can use to solve certain types of electrostatic problems. And of course, we relate that to circuit theory that you're more familiar with. And the minimum level of understanding that you should have in this context is you should be able to calculate voltage from electric field, and you should be able to calculate the electric field from the potential difference. You should be able to calculate the potential difference from the electric field, and you should be able to calculate the electric field from the potential distribution. And so that's the level of understanding that we want you to have at the very minimum level. But there's much power in being able to use the potential difference to solve complicated electrostatics problems. So the first thing I want to very briefly touch back on is the idea of electric force. So we know that we saw in the last lecture that electric charge experiences a force that is proportional to its intensity, that's proportional to the electric field intensity and the charge on the particle. And so in this case, if I have a charge that comes in contact with an electric field, and that charge has a positive quantity, it's going to be deflected downwards as it travels through because it has a force that's applied to it. Right? So that's fairly straightforward. And if I want to think about the idea of taking this charge, and let's say I have this charge, and that charge is located in some other position. So I have a charge down here, and I want to move that charge from point A, and I want to move it up here to point B. In order to move that charge from point A to point B, I have to do a certain amount of work. And that's where the concept of potential comes from. It is the amount of energy, it's related to the amount of energy that it would take to move a charge from point A to point B. Right? So that's where the idea comes from. So it's related to the concept of potential energy in an electrostatics fashion. There are two fundamental postulates that we're going to exploit in dealing with electrostatics. And these are postulates that can't be deduced from other postulates. So they're just basic principles on which we're going to build the rest of our theory. The first is that the curl of the electrostatic field is equal to zero. It means that the electric fields are irrotational, and we're going to find out what the physical consequences are for that in just a second. And here's an example of a non-irrotational field. Right? So you can't produce a field like this in electrostatics. The second is that the divergence of the electric field is equal to rho over epsilon. This is Gauss's law. We talked about this already in lecture 1. And this tells us that electric field lines must begin and end on charges. We can relate this to flux. Now I want to make a note. In today's lectures, we're going to be talking almost exclusively in terms of the electric field intensity E. In lecture 4, I'm going to introduce the relationship between the displacement vector D and the electric field E, and in many problems we're going to find that displacement vector is actually powerful to be able to use, but today we're just going to concentrate on focusing on the electric field. So let's look at a little bit of what the consequence is. I can invoke Stokes' theorem, and Stokes' theorem allows me to integrate over a surface. So I've got here a double integral over some surface A of this curl dotted into the surface area element. Right? So that's Stokes' theorem. And when I compute that integral, I can turn this area integral into a line integral around the perimeter of the area, and I end up with this expression here. So I have a closed integral around a contour of the electric field dotted into the length integral. And Stokes' theorem tells me that this must be equal to 0. So if I do an integral that starts at a point and finishes at the same point, I get 0. And it doesn't matter what path I take to get there. So I could integrate here, okay, and I'm going to get 0. Or I could integrate here, I'm going to get 0. Right? So it doesn't matter how I get from that point back to itself, it means that the potential is equal to 0. And I can exploit this fact to define a field distribution that we call the potential. And it's a scalar field, unlike the electric field that's a vector. And there's a little bit of a trick here. You recall from your first calculus class that when you do an integration, you always end up with a constant of integration. So if you integrate x dx, you get x squared over 2 plus a constant. Okay? And that constant, you choose it in order to be able to satisfy the particular details of your problem. What we're going to do is we're going to pick a location in space that we're going to define as having potential equal to 0. Okay? Sometimes that might be the origin. Oftentimes it's off at infinity. Okay? But there's some location that's defined as having 0 potential. If I then integrate from that 0 potential point to an arbitrary position r, this line integral, that then defines the distribution of potential everywhere in space. So here is my closed path integral, which gives me 0 field, and this is my point that I'm going to begin at, my r0. And I have a little differential length element, and I integrate around this path, I get nothing. Okay? I can integrate from another starting point, I get nothing. Okay? But if I integrate from, say, point A to point B, I'm going to get some potential difference. Okay? And if we define this as our 0 potential point, then the voltage at this location, or the potential at this location, is given by this integral. If I then integrate to another point, the voltage at position B is given by the integral from 0 around to B, not from A to B, but from 0 around to B. Okay? And VB minus VA, right, so that's the potential difference between these two locations, that's given by the difference in these two integrals, and that's what's highlighted here in purple. Right? So this first integral is the integral from point 0 around, the second integral is the integral from 0 to b. When I subtract those two integrals, VB minus VA, that gives me this potential difference. Okay? And we can relate the electric field to the potential distribution through this gradient. Right? So we have this powerful tool that the electric field, E, which is a vector, of course, is equal to minus the gradient of V, right? And so when I plug this into this expression here, the minus sign cancels, and I end up with this expression. And this, in many problems, and we're going to see this in lecture 3, in many problems it's much easier to compute the potential from a given charge distribution than it is to compute the electric field directly. So we'll take a look at an example of this. Let's say we have Coulomb's law that we talked about in the last lecture, and we have a collection of charges. Here we have 4-point charges, and I want to know what the force is on some test charge, capital Q, at some distance. Okay? Well, the force due to the first charge is given by 1 over 4 pi epsilon naught Q1 times capital Q over D1 squared, and it's in a particular direction. Right? It's going to be in this direction. Then the force due to the next charge is going to be in a slightly different direction. And I need to add these forces up, keeping track of both their magnitudes and their directions. And this is a fairly complicated activity. It involves doing trigonometric identities, and a three-dimensional geometry can be extremely complicated. Okay? The total electric field is given by the force divided by the magnitude of our test charge, and we have this summation. Now, this is straightforward. You can plug it in. You can program it in a MATLAB or into a calculator, and you can get the answer to be spit out. But it can be tedious. You need to keep track of the terms. We can define the potential at this position as the integral. In this case, we're going to set our 0 potential point to be at infinity. Right? So if I get far away from my charges, I know my fields are falling off like 1 over r squared. And so if I move from very, very, very far away, and then I move a little bit closer, but my electric field is almost 0, I have no work, so there's not much potential difference there. But as I get closer and closer and closer to my charge distribution, I have to do more and more work. So for this problem, we're going to find our 0 point, our reference point, as being off at infinity. And I can compute the potential due to one of these charges as the integral of 1 over 4 pi of the electric field dr. Well, when I do this integral, I integrate 1 over r squared, and I end up with 1 over r. I substitute in di, and that gives me the potential due to each of the individual point charges. And I can add them all up to get the total potential distribution. And it's much easier to do that computation, and we're going to exploit that in one of the lecture 3 lectures to talk about dipoles. The last important concept that I'm going to emphasize in today's lecture, is the idea of capacitance. And you, of course, are familiar with working with capacitors in circuits, and you know the capacitors are used to store electric energy. They're used to store charge. You know how you can treat a capacitor in a circuit element, how you compute the capacitor for a particular, the impedance of a capacitor for a particular frequency. We're going to talk now about how this quantity of capacitance is actually related to the electrostatic fields. And so let's look at a very simple example. Look at a simple example of a parallel plate capacitor. And we're going to assume, in this case, that the plates, which have area A and are separated by a distance d, are such that the width and length of the plates is much larger than d. So it's not really reflected here in the picture. In reality, we're going to assume these plates are much closer together. And what that allows us to say is it allows us to say that the fields between the plates are approximately uniform. When I get near the edges, my fields are not going to be uniform. My fields are going to bend, and I'm going to have what's called fringing fields. But we're not going to worry about that. We know how to solve that problem, or I know how to solve that problem, but it's well beyond what we need to worry about for this course. So we're going to assume that the fields are uniform. And we can use Gauss's law to show that the fields in this particular case can be related to the surface charge density. And we can write the electric field as minus rho sub s divided by epsilon in the z direction. So my electric fields point from the positive charges to the negative charges. Here I've denoted it as d, but we'll find out in lecture 4 that d and e are proportional. And so I've got a plus rho s on the top. I've got a minus rho sub s on the bottom. Okay, so equal and opposite charge separated here. I have a total charge q on the top and a total charge minus q on the bottom. Okay, and of course q is equal to rho sub s times a. And this is the value of my electric field. We know then that we can define the potential difference between the top and the bottom plates in this way. So I'm going to integrate from 0 to d, and I'm going to take the dot product between my electric field, which is pointed down, and my dl, which is pointed up. So those two vectors are in opposite directions. So I'm going to get a minus sign, which is going to cancel that minus sign. And when I do that, I get, plugging in this value, this particular integration, right? So I have a constant dz, and that's going to give me rho sub s d over epsilon. Now, capacitance we define is relationship between the voltage and the charge that's stored in the capacitor. Well, rho sub s is equal to the total charge divided by the area, right? So I have this relationship between the voltage and the stored charge, and we define capacitance in this way. Capacitance is equal to q over v, and in this particular case, it's epsilon a over d. So that is the capacitance of a simple parallel plate capacitor when I can ignore the effect of the fringing fields that are actually outside the plates. Right? Those fringing fields are going to make a small correction onto this computed capacitance. The last example I'm going to do is a coaxial line. So this is a slightly more complicated problem, but it's one that's very important to us because when we talk about transmission lines, we're going to want to understand how the capacitance and the inductance are computed. The electric field in a vacuum-filled coaxial line can be computed this way, and I do that using Gauss's law. So I assume I have a certain amount of charge on the line. I draw my Gaussian surface, and I can get the electric field, and I can write it this way. So it's proportional to the total charge. L is the length of the coaxial segment, so I'm going to assume that this has a length L into the screen, right? So it's going to be some finite length of coax. And so Q over L, if you will, that's like a line charge density. It's a charge per unit length. And this is what my electric field is. And my electric field is pointing, say, in this direction. If I have a plus Q on the inner conductor and a minus Q on the outer conductor. The next step to determine the capacitance is I need to know what the voltage difference is. I need to know the potential difference between the inner and the outer conductor. And so I do that by taking the integral from radius A to radius B of the electric field dl with a minus sign. Okay. Well, I know what my electric field is. It's Q over L 2 pi epsilon naught R in the radial direction. Okay. And my integral is r hat dr. Notice I'm taking this as being positive. My limits of integration are going from radius B to radius A. Okay. dr will then be a negative number, but I don't put a minus sign here. Okay. Now, we know from our rules that r hat dot r hat is equal to 1. That goes away. I can factor out this Q over L 2 pi epsilon, okay, and I'm left with Q over L 2 pi epsilon naught, the integral from A to B of dr over r, where I have now gotten rid of this minus sign by flipping my limits of integration. Instead of integrating from B to A, I'm now integrating from A to B. And that allows me to change the limits, change the sign, which of course gives me the natural log. And from this, we can compute the capacitance, which is the ratio of the stored charge to the potential difference. And that is given by this formula here. And we're going to find out later on the quantity that we may be interested in is actually the capacitance per unit length. So I take C divided by L, and that gives me the capacitance per unit length of a coaxial cable. So if I double my coaxial cable's length, I double the amount of stored charge for the same potential difference, so therefore I double the capacitance. If I half the length, I have half as much stored charge for the same potential difference, and so I have half the capacitance, and so on and so forth. So that brings us to an end of this lecture. And in the tutorial on Tuesday, we're going to talk about applying Gauss's law to help us be able to compute the electrostatic distribution for geometries, and then using those fields, we're going to compute the capacitance.